Okay, we're going to begin continuing in 12.7, spherical coordinates. A couple more examples. Yeah?
Are you going to go over this topic 6?
Do we have homework for 12.6?
Yeah.
Okay. Okay, questions on 12.6?
Number 1.
Number 1, narrow angle. What does that look like?
Yeah, I really didn't know how to do that. They give us a point in cylindrical coordinates.
They what?
They give us a point in cylindrical coordinates.
Okay, so we have a cylindrical coordinate point. Okay.
The point is 4 pi over 3 negative
4 pi over 3 negative 2. Right, this is r theta z.
2.
Yeah?
That's the plot the point and the plot with the next one.
Okay, so plot is kind of stupid. And change to rectangular. Okay, so in 3 dimensions, so in the xy plane, I'm going to have an angle of pi over 3. I'm going to move a distance 4 units from the origin, and then I'm going to go down -2 on the z-axis. So, look like that. In rectangular, what would I do? Well, rectangular means I need to go from r theta z to x, y, z. But in the xy plane, what's going on? That's what's going on in the xy plane. So then I just find the xy coordinates of that position. So how would you do that?
X is 4 times cosine pi over
X is 4 cosine pi over 3. Y is 4 sine pi over 3. So you just use the equations, right? You know that x is r cosine theta and y is r sine theta. Cosine pi over 3 is what?
1.
This is 2. Sine of pi over 3. So this means the rectangular coordinates is 2 comma 2 radical 3 comma -2. Okay, other questions? Yeah, just use the formulas for polar coordinates. And in the next section, in 12.6, I believe there are also problems like this where you're just going to use the formulas for spherical coordinates to find the x, y, and z. Other questions? 25. What does that say? Find the volume of the region E bounded by the paraboloids blah and blah. So that x squared plus y squared and z equals 36 minus 3x squared minus 3y squared. For A, I need to find the bounded volume. Draw a picture. X, Z. One is a paraboloid going up like that, the other one is a paraboloid going down with maximum 36. So that's the object. Okay. What do I do now? It's kind of off, but whatever.
You could find points where they intersect, so you.
Right, I need to find the intersection so I can figure out a region of projection, because that's how the two outer integrals are going to be set up. So figure out the intersection. Which means I need x squared plus y squared equals 36 minus 3x squared minus 3y squared, which means that x squared plus y squared is equal to what? 9. So just circle radius 3. I can describe this as r going between 0 and 3, theta going between 0 and 2 pi, and my z going between r squared, which is the bottom surface, up to 36 minus 3r squared, which is the top surface. This means my volume is equal to the triple integral over this surface of 1 dB, 0 to 2 pi, 0 to 3, r squared up to 36 minus 3r squared of r dz dr d theta. It's going to be 2 pi times integral from 0 to 3 of r times 36 minus 3r squared minus r squared. This clock is cold. So that is 36r minus 4r cubed. So this, what? 18r squared minus r to the fourth, and 0 and 3. So I'm going to get 2 pi times 18 squared minus 3 to the fourth.
162 pi.
And that's what?
162 pi. And
Like everything
yeah.
is 162?
I know it's going to be within the wording of the problem, but how would you know specifically when you have to use 1 dB or when you have to subtract the top surface and the bottom?
They're both equivalent.
They're both also the same expression.
Yeah, because here you'd have bottom here, bottom surface is here, and top surface would go here, which when you integrate with respect to z, you're going to plug in top minus bottom. So this is actually equal to the double integral of top minus bottom. dA.
And we can
You'd realize that that's what happened here. This is the top minus the bottom.
And the R. Okay.
So you can think of it as the double integral of top minus bottom or the triple integral of 1. Either way, you'll get to the answer.
Yeah, so we can use the double integral, unless it says use triple integral, we can use double integral.
Yeah, it'll be up to you. Unless it specifically asks for a triple integral, you can think of it as a double integral. It'll be the same. There was a part B. Find the centroid. Center of mass case where the density is a constant. So this is 25. Part B. We're after the centroid. Density equals K, that's just a constant, which means it's uniform, which means there are two pieces of information I already know. What's that?
You know the mass?
Volume.
You know the mass? If you just add K to the 162.
In regards to the centroid.
You know MY, I think?
X and Y? Is there
I know X bar and Y bar. What are they?
Is there
By symmetry. And so the only guy that's missing is Z bar. That's going to be 1 over M times the triple integral of the density. dV. So now I'm going to have to find M, which I know is just, oh, this is Z times the density. Now I'm just going to have to find M, which is the triple integral of the density. dV. Which,
Because it's a constant, you can just multiply by that.
right, so we actually did the volume, which is just the integral of 1, so I just multiply that answer by K. So here, pi part A, M is equal to 162 pi times K. This means my Z bar is going to be 1 over 162 pi K times (0 to 2 pi, 0 to 3, r squared up to 36 minus 3 r squared times Z r K dz dr dθ.
Wait, can you say it again? How do you get 0 and 0 for the
Symmetry. It's symmetric about the
Oh, okay.
origin. Right. In the xy plane, I just have a circle of radius 3. So because the density is uniform, it's just going to be smack dab in the center. Remember, the centroid is just the center of mass. It's the balance point. Because the density is constant, it's uniform everywhere. The balance point is just going to be in the middle. Right. So as far as x and y are concerned, I know what the middle is. As far as this is concerned, I'm not sure because the z is not symmetric. So that's what I'm trying to figure out. So k's would cancel. In this case, I'm going to have z squared over 2 and I have to plug this guy in. So I'm going to have 2 pi times 1 over 2 times 1 over 162 pi times 0 to 3. 36 minus 3r squared squared minus r to the 4th all times r. One over 162. Yeah, this is just a matter of expanding and multiplying out. So 36 squared minus 6 times 36 r squared plus 9r to the 4th minus r to the 4th. All of that's going to be times r. So this is r, that's r cubed. This is 8r to the 5th. Squared over 2r squared minus this 6 times 9 to the 4th plus 8 over 6. And what was that?
It simplifies to 15, but you got really good numbers.
It simplifies to what?
15?
The whole thing? Like the whole
Yeah.
answer?
Yeah.
Just 15?
After you add like
Yeah, yeah.
thousands together.
Okay, so the centroid then is just 0, 0, 15. Other questions?
I remember 13.
13. I don't have 13 here. Okay, so we're just going to be well, it's not really to even do any integrals, really. You're just going to describe a cylindrical shell that is 20 centimeters long with an inner radius of 6 and an outer radius of 7. Write inequalities that describe a shell in an appropriate coordinate system. Okay, so personally I would have put the shell just sitting on the XY plane. So I have an inner radius of 6, outer radius of 7, and my height is 20. And I just need to describe the shape using, so I just can set z goes from 0 to 20. R goes from 6 up to 7. Theta goes from 0 to 25. That's it. This is in cylindrical coordinates. Coordinates with axis along the z-axis and base on xy. They say how you set it up. So I can just set up my cylinder so that the axis runs along the z-axis and the base sits on the xy plane. And in that situation, this is how I would describe that cylinder with a bunch of inequalities. Well, there's a couple sentences. You write this down and you write that down. Yeah, that was sort of an exercise in if you have to like set up the limits of an integral to integrate over an object like that, this is how your limits would look. Other questions? How much time do we have? Let's move on. For the most part, you guys seem comfortable with this stuff. So we're just going to finish up 12.7. We just have a couple more examples to go. You can pass your homeworks up to the front. Then we're going to start talking about sequences, which will be a very easy topic if you remember your limits. But it's going to be a lot of definitions that I have to remind you about, so we're going to do a lot of writing when we do that. All right, let's continue with 12.7. I did that example where we did that cosine of x squared plus y squared plus z squared. I believe I also asked you about the volume inside that shifted sphere and the cone. Okay, so here's a problem. I've seen a similar problem to this on a past final, and I'll probably put a similar problem to this on the next test. So what I'm going to do is I'm going to describe a region. I'm going to ask you to set it up. So let T1 be the region above below the xy plane. Above z equals that is inside the sphere. I'm describing several regions here. I missed the T1 is the region above this. That is inside x squared plus y squared plus z squared equals 1. Let T2 be the region So those are my two regions. Here's what I want you to do. Set up two integrals. Set up the triple integral over the object T1 of x squared plus y squared plus z squared dv. And triple integral over T2 of x squared plus y squared plus z squared dv. Use coordinate systems of your choosing. On a test, I'd probably ask you to also evaluate either one of them. Okay, let's talk about the triple integral over T1. How do we set that up? Or let's draw it. What do we look like? What does z equals minus the radical of x squared plus y squared look like?
It's on in the negative there.
Cone going down, opening like that. Okay? That is inside x squared plus y squared plus z squared equals 1. What's that? This is unit sphere, sphere radius 1, centered at the origin. So what do I want? I want it to be above z equals blah and inside the sphere. So what region am I talking about? Outside of the cone and inside the sphere, right? So it's this whole thing here. So that's the region what we're talking about. So it's like a sphere, but I drilled a hole in a conical shaped hole in the bottom of it. Okay, so set it up. Coordinate system of your choice. You use spherical. Why would you use spherical? This is a part of a sphere. Okay, so that's a sphere. So you'd think spherical would be easier. So my choice would be sphere. We can probably set it up also with cylindrical if you want. Rectangular is clearly going to be like a nightmare. So, how is the setup? How does spherical work?
Theta from 0 to 2 pi.
Our theta would go from 0 to 2 pi. That one's easy. That one we know from polar coordinates, so we should be pretty easy to see that one. Okay. Phi goes from 0 to, how do you know that?
It's like it goes from the z-axis down.
Right, so it starts here from the z-axis and it goes all the way down until it hits this guy. That's clearly 0, and how do we know that this is 3 pi over 4?
Because it's like, y would, if it was to stop at the y-axis, it'd be pi over 2. So they just add pi over 4, which would be 3 pi over 4.
Why do you know it's pi over 4?
And it's like,
It just makes
with
sense.
the,
It makes sense.
This is in the YZ plane. From the graph of the cone in the YZ plane.
You
Y
have to do the
equals
intersection.
Z equals negative Y.
If that the regular axis stays at 1 for 1, that would have to be that.
From the equation of the cone, when x equals 0, Z equals negative Y.
From the equation of the cone, when x equals 0, you said?
Yeah. Then Z equals negative Y.
Alright, so like take pi, right, and then minus pi over 4. Alright, so it's going to really be like 4 pi over 4 minus...
How do you know it's pi over 4? That's basically what I'm asking. Yeah, so you're basically claiming that this angle here is going to be a pi over 4, so
Yes.
clearly that has to be 3 pi over 4. But
Yes.
how do you know that's a pi over 4?
I think the equation of the
Right
cone
there.
is plugging the spherical substitution. Like
Yeah, you can do this guy and plug in the points, right? You can replace this with rho cosine phi. This is rho cosine phi, rho cosine theta sine phi, rho sine theta sine phi, and you can actually solve for the angle. You can get that phi equals pi over 4 from this, which you just take the reference angle. That's one way to do it. I just want to make sure you know how to do it. So if I did something like that, that would be fine, right? Something like that wouldn't be a problem,
Oh, so we know how to
right?
get
It's not. I need you to know how. Okay. Okay.
Can you clean it again?
Hmm?
Can you clean it again?
Like you start with the equation of the surface that you're considering. This is the algebraic way to do it. And you just plug in the spherical coordinates. So this side would plug in rho cosine phi. Here I would plug in, for x it's rho cosine theta sine phi. Plus the y would be rho sine theta sine phi. Rho sine squared phi is a common term. When you factor that out, you're left with cosine squared plus sine squared, which becomes 1. So this pretty much comes down to rho sine phi. So this is rho cosine phi equals rho sine phi. You cancel. So you basically want where tangent is -1. Right? So this would give you that tangent theta, tangent of phi is -1, which, so you know this is in Q4, but you have to,
Would it be cotangent?
it depends on who you divide by who. I brought the cosine over here, and that's what I used. But you do know that's in the 4th quadrant, where this is pi over 4. You know that this here is pi over 2, so together it's 3 pi over 4, things like that. Right, so you can do it algebraically, like you can also draw pictures. I just want you to know how to figure that out, just in case I give you something weird. Okay, but yes, for the cone z squared equals x squared plus y squared, pi over 4 is always going to be the angle from the center here. Okay, so what about rho?
0 to 1.
Yeah, it's the distance from the origin to the outer surface, right? Which at any point, it's going to be 1 because it's a sphere centered at the unit sphere. So the setup would be the triple integral over T1 would just be 0 to 2 pi, 0 to 3 pi over 4, 0 to 1. What does x squared plus y squared plus z squared become?
Rho squared.
That's rho squared times dv, which is
Rho squared. So d over 2.
that's your answer for T1.
So where'd you get the first row squared?
Come again?
Where'd you get the first row squared?
From this, I asked you to integrate x squared
Oh,
plus y squared plus z squared.
Oh, I didn't see that.
Jhevon, tell me how to set this up in cylindrical. I wouldn't, but let's say that was your choice. How would you actually do that? Cylindrical. Hmm? Well, the theta is going to be the same, obviously. What about R?
It's also the same.
It's going to be the same as rho in this case, 0 to 1. What about your Z?
0 to
Nope.
You just gotta equal the z switch.
So they call 1 minus r squared plus 1.
Radical of what?
1 minus r squared.
Yeah.
Because x squared plus y squared plus z squared it was 1. That's the equation of the sphere.
Okay, so where do I write?
Bottom part is negative radical x squared plus y squared.
Yeah.
X squared, or r squared, sorry.
No, no.
Negative r.
Is equal to negative r.
And then this would be what?
That would be z, the square root of z minus r squared, right?
No, 1 minus
Square
r.
root of 1
squared.
One minus r squared.
1 minus r.
Oh, yes, there you go. Yeah.
Is that right?
No, that's
No.
negative radical 1 minus r on the left.
No. The bottom is the cone.
No, 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 good.
It was good before you had it set up.
Yeah, it's minus r.
It was good how you had it before.
Minus r squared. Minus r.
Exactly. So that's wrong.
Yeah.
If you guys set that up, that would be wrong.
You just do the volume of the sphere and then the volume of the cone is correct.
You can't do that because you're integrating something. It's not like you're integrating a constant. So yeah, that would be wrong. For cylindrical, you would need 2 integrals. So if you had made that choice, you would have probably realized pretty quickly that that's probably the wrong choice, because that's just too hard. Why was there 2 integrals?
Oh, you can face the left side of him as the right side of him, pretty much?
Look at this intersection here, right? Look at this point, right? And sort of follow this up. Right? Now, if I'm a little man trapped inside the shaded region and I look down, what do I see over here? Sphere. If I look up, what do I see? The sphere. If I'm over here, though, if I look down, what do I see? The cone. What do I see if I look up? The sphere. My top and bottom switches. I would literally have to set up a different integral for this region. I have to figure out where they intersect, find the region of projection, and I'd have to integrate over that circle where the bottom function for z is r and the top minus r and the top function is the sphere. And then outside that circle, right, I'd have to find another circle, which is obviously radius 1, and I'd have to do, it's going to go from minus the radical of 1 minus r squared to the positive radical of 1 minus r squared. Right? So cylindrical would actually give you 2 integrals here.
That's
You
terrible.
have to be very careful. Right? Whereas spherical, 1 integral, all limits are constants. You don't have to worry about functions in your limits, right? So spherical was actually a much better choice in this case. So there are 2 things to worry about. It would be annoying to set up cylindrical, and you might have missed that thing, but you shouldn't though, because you should always be looking for the top and the bottom. Okay, let's talk about T2. I described that T2, the region above that same cone, right? So I'm going to draw that negative cone again. Below the xy plane, but inside x squared plus y squared equals 1 is what?
I'm the cylinder.
It's a cylinder running along the z-axis, right, circular cylinder, and I need to be below the xy plane. So here's my xy plane. I need to be below that. So basically, I'm going to be the area under here. Hopefully you saw that. So we are above this guy, so this is our cone. The shaded region must be on top of that guy, but at the same time must be below the xy plane while contained inside the cylinder. So that's our shaded region. What coordinate system would you use? Right, because this is a cylinder. Cylindrical is what I would do. How do we set that up in cylindrical?
Theta would be 0 to 2 pi, obviously. R would be
0 to 1.
Yeah, those two are pretty normal. What's the lower part?
Negative square root of x squared plus y squared. So
Negative r, right?
Negative
Because that's
r.
the cone that's on the bottom. On top is the xy plane, right? What's the equivalent of the xy plane? 0. So those are my z limits. So the integral set up around t2 is just going to be 0 to 2 pi, 0 to 1, minus r to 0. What does x squared plus y squared plus z squared become? R squared plus z squared times, what's my dv?
Already did.
R dz dr d theta. So triple integral. So that would be the setup. For fun, circle. What's the spherical setup for this? Theta is 0 to 2 pi. What?
Pi is from pi over 2
What's-
to 3 pi over 2. At 3 pi over 4.
Pi over 2 to 3 pi over 4. Do you see why? Because it's going from the xy plane, right? That's where it starts measuring. Remember, 0 is at the z axis. By the time it hits the xy plane, it's already at pi over 2. But that's your start, right? So it starts at pi over 2 and it continues to go down until it hits the cone, which we've already discovered last time that was 3 pi over 4. Okay? What about the row?
no. Because the whole point we had the first integral was because we had the top half. This is below the xy plane, so it's just the bottom half. Yeah.
What is the row?
Confound function.
You'll always be true.
So here, again, if I'm looking at the xy plane, my z-axis is here. There's a cylinder coming down. There's boom, boom. Here's my shaded region that I would care about. Right, so my phi was extended from pi over 2 to 3 pi over 4. What is the rho? It's the distance from the origin, right? I need the distance from the origin that's hitting the outer surface. What's that going to be?
No. It's variable.
It's variable, because what if I hit out here? That's clearly a different length than the previous one, right? What am I hitting? What am I measuring the distance to? The cylinder, right? So I need to somehow measure the distance from the origin to the cylinder. How am I going to do that? So it clearly starts at 0, but it's going out to the cylinder.
Wait, could you sub in the could could you sub in x squared plus y squared equals 1 into the cone function, like z equals negative square root of x squared plus y?
So the cylinder, no, what is the cylinder then?
Why don't you change that? X squared plus y squared equals 1, that's the cylinder.
X squared plus y squared equals 1. That's the surface I care about.
Yeah, and the cone is z equals negative square root x squared plus y squared equals 1, so you could just make that 1.
Yeah, but that's,
Figure out 1.
that wouldn't help. This surface is irrelevant,
Okay.
right? The distance is always measuring to the cylinder. The cylinder is the guy I care about. What do I do with it?
Convert it.
Huh? Yeah, just sub in the circle. What's x? Rho cosine theta sine phi plus rho squared sine theta sine phi equals 1. So this means, again, this just means rho squared sine squared phi equals 1. Which means what? Rho is just 1 over sine phi. 1 over sine? 2 rho? Where?
Yeah, you shouldn't have you added the two then together.
Come again?
Your cosine, your functions of theta cancel, and you're left with.
Nah, you factored out the rows and then made.
No, I factored out rho squared sine squared phi. It's a common term. I factored it out. I'd be left over with cosine squared plus sine squared, which becomes 1. And I have that. Take the square root of both sides. Rho is a distance, so I'm just taking the positive square roots, and then I divide by the sine. 1 over sine is cosecant. So basically, I wanted to write the equation of the cylinder in terms of spherical coordinates, which we actually practiced a little bit of that last time. Or you just substitute your expressions for x and y. Right? So the first thing is to figure out what surface am I actually measuring the distance to, right? You can write it down in rectangular and just sub in your equations to find out what it is in spherical.
So that's always the way to find out the density, basically.
It's one of the ways, right? You could use like trig otherwise, yeah.
How do you find the P from pi over 2 to pi over 4?
Oh, for the same, that's the picture we're looking at, right? So we had that cylinder here, and this was the z-axis, and then we had that cone. Last time we saw that the cone, the angle here was pi over 4, right? Phi starts at the z-axis, phi is 0, right? Which means by the time it hits the xy plane, at this point, phi is pi over 2, right? But that's the start here, right? I'm starting at the xy plane. So I start at pi over 2, and I continue here, right? So this is 0, pi over 2, and this angle here is pi over 4, then the whole angle is 3 pi over 4.
So we do it only for one side, 0 to pi.
Yeah. Like, I only care about one side with the phi. The theta is what will swing him around, so I don't even have to care about any other side. Just think of it in one plane and just figure out what the phi is doing. Just draw a 2D diagram.
Shouldn't rho start at 1?
No, rho has to encapsulate all the shaded regions, so there is a point that's right beside it.
I thought it just is like the outer edge, like the outer part.
No, rho is a range. It has to encapsulate all the shaded region. Yeah, if rho was just 1, it would literally just measure to here.
Yeah, that's right. Yeah, and then I thought, and then it goes down in terms of.
Yeah, but what about a point like here?
Well, that's what's covered by the theta and the phi. But like that whole point of it is like.
No,
rho
because
is the
here,
outer edge.
every point along this line, your phi is pi over 2. This does not change according to phi. It also doesn't change according to theta.
Okay. Yeah.
So we have to go from the origin all the way out is what we care about. So when you're at the origin, you're at 0, and you extend to the cylinder. So I start at 0 and I extend to the cylinder. and I just write that equation of the cylinder because I figured out that's the surface I need to care about. Plug in my expressions, change it into spherical, so that's the case. And finally, let's just do it right here. The triple integral over T2 in spherical would be 0 to 2 pi, pi over 2 to 3 pi over 4. Rho is 0 to cosecant phi of rho squared sine phi. So we don't need two integrals here, but it was kind of annoying setting it up.
Isn't it 0 to 3 pi?
No, because you start at the
No,
XY.
I start at the XY thing. Remember, this is my shaded region. I'm starting here and extending here. D rho, d phi, d theta. So I wouldn't have done it this way. It's not super bad, but it's more annoying than cylindrical, I would think. How would you actually integrate this one? Because this would be rho to the 4th. The integral would be rho to the 5th over 5, right? Then I'm going to plug in a cosecant. If I got a cosecant to the 5th times a sine,
Cosecant.
Cosecant to the fourth.
okay, so we'd write that as cosecant to the 4th. And how would you integrate that?
Hold on, I'll tell you in like 2 seconds. Let me just look at that.
Gotta review your calc 2.
Is he right here? It's not 100?
Yeah. I should put that on the test now, see how many people get it.
Please don't.
You should put it on a reference sheet.
Yeah, well, that's it for integrals. Yay! That's it, yeah. So we've covered iterated integrals, learn how to take double and triple. The same sort of thing extends to if we're going to 4 dimensions and higher, but we won't talk about that because we don't care. Which reminds me, a couple people are emailing me asking me about 391 versus 392. I guess registration just started like yesterday for a lot of people. So, as I said before, if you can only take one of these classes, it's not totally crazy to take both of them. That's if you're not doing anything else that's horrible, like physics, right? But if like if you're doing like physics and then like a hard engineering class and then you take 391 and 392, probably not a good idea unless you're really good at math. But if you only have to take one of them, I would take 392 first. Probably kind of counterintuitive. So 391, this is differential equations. 392, this is vector calculus and linear algebra.
Would you advise taking both at the same time?
I just said if you don't have any other hard classes, yes.
Okay, sorry, I was.
So do this first.
Is it just because you're
Regardless of what your advisor says, do that first. An advisor that tells you, oh, you should do this first, don't know what they're talking about.
Yeah,
There's a lot of Calc 3 in this. 2/3 of this course is Calc 3.
they told me to do.
Like if you forget your Calc 3 when you hit this, you're going to have like a horrible time. If you're strong in your Calc 3 when you hit that, easy. Like hardly any time on homework or anything. Well, depending on the professor you have, but it's going to be like easy for you to catch on. You're going to be setting up double integrals, triple integrals, you're going to be graphing surfaces, you're going to be sketching vector curves, you're going to be finding tangent planes, like all the things, a lot of the things that we talked about. You're going to be doing the same thing. just a slightly different context with different formulas, but it's 2/3 of that class is Calc 3.
You recommended Rawlings for that, right?
Yeah, Rawlings is good for that.
Why don't they ever put up like the teacher for that?
They actually don't know yet.
Okay.
So they're always just late, like deciding who. Like I don't even know who's teaching what. Anyway, so I don't know what I'm teaching next semester yet. So, but yeah, if you're deciding, 392 is what you should take first. 391. It's mostly going to be new stuff. There are a couple things from Calc 3 in there, but it's not really. There's like a couple places where you take partial derivatives, like, you know, and then there's a section on series in here, but it's not going to feel like anything like the series we're doing here. Like what we do here in series isn't really going to help you there.
Would you say that that's easier or harder than Calc 3?
What?
Differential equations.
I found it easy. It feels a lot like Calc 2. Feels like Calc 2. So I don't know if some, I liked Calc 2. It's a lot of drills, that's what it's like. So it's like, here's this kind of differential equation, here's how you solve it. Do a bunch of problems, so you just get that step down. Here's another kind, solve it. Here's another kind, here's how you solve it. Here's another kind.
Basically.
Yeah, so it's kind of like Calc 2 when they're like, this is integration by parts. Here's how we use it. This is integration by partial fractions. Here's how we use it. This is integration using trig sum. Here's how we use it. It's going to feel a lot like that. It's just a bunch of methods to solve certain kinds of equations.
Isn't it just all math?
Huh?
Isn't that what we always do? All the time?
Yeah, it sounds somewhat similar.
No. Like, Calc 3 is not like that.
No, it's just like you give us like a problem, it's like this is how you solve it, then we solve it.
Not really. You sort of have to like figure things out more, I think.
Oh, you're saying that's more like formulaic? Like,
It's more like formulaic. Like you don't have to visualize anything usually.
Okay.
Like it's just like
But like with Calc,
I know that formula, so I'm just gonna do it.
but like with Calc 2,
Yeah. So it's just a lot of like just memorizing and just drilling through problems. That's what it's gonna feel like, at least here. There are a lot of graphical applications to differential equations, but we don't really focus on it here. It's just going to feel like just know a bunch of formulas in your head and methods and you just crunch them out. That's what it's going to feel like. 392 though, you're going to have to be drawing things and you're figuring out what side of the surface is it, and then you're going to be planting normal vectors and you have to worry about what direction the normal vector is in. Right? So you can literally know all the formulas here and still mess everything up. Right? It's that kind of thing. But it's like, it's mostly Calc 3, right? So it's like, if you draw your surface wrong, even if you know all the formulas, you're going to get the wrong answer, right? Whereas that never really happens here. It's just like, this is in the form to use this formula. Just use it.
Okay.
You know? That's what it's going to feel like. So it's a lot like Calc 2, but this one you really need a lot of Calc 3 for it, so it's a bad idea to let too much time go between Calc 3 and taking that course. Let's move on. We're going to move on to chapter 8. 8.1, where we're going to talk about sequences first. Series start at section 8.2. Yeah, if you were late, I gave a table of the tests. It's nice to just have them all in one place. I don't know, some older version of Stewart's Calculus had a table like this once upon a time, but then one of the newer editions like took it out. I don't even understand why.
it's in the second edition, I think. But like the third one.
Yeah, so I actually just stole this from another textbook that has all the tests in one place. How you're going to want to deal with series is, again, sort of similar to Calc 2. It's just like you're going to recognize a form. You know, well, the series look like this, so I should probably use one of these, right? There's going to be here you see there's a test that we're going to use, and I'm going to say when to use it. If things look like this or blah, 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 then you use it. This is the conclusion you make. So it's a really nice table to do it with. When I was doing Calc 2, I just did my homework with this table beside me. Eventually, after going through a bunch of problems, you memorize it, which you have to memorize. Like, I'm not going to give you this. You're gonna have to know all this in your head. So, just spend a lot of time on your homework with this right beside you. Keep checking it. After a while, you'll remember it. It's not actually not that bad. It's a lot easier than you think. Once you get over the fear factor. What is this? No, I want integrals back. Sequences. Let's just jump into it. How we're going to think of it is a sequence is an ordered list of numbers. That's basically how we're going to think of it. Each number in the sequence is called a term. Right, so I can talk about the terms of a sequence. It's just the numbers in that sequence. The place of this, of a term, is identified by a subscript. Let's talk about the notation, how we're going to write these down. We can name sequences like functions. In fact, sequences are functions. An alternative definition is to think of a sequence as a function from the natural numbers to the real numbers or complex numbers. Sequences are named by letters with subscripts that define the independent variable. For example, I can write a sequence like a to the sub n, right? This is the sequence A. Or I could say B sub n. That's just the sequence B. We may denote the start and end by, I can say something like here. Here's a sequence AN, where my n is starting from 1 and it's going up to infinity. This is called an infinite sequence. So an infinite list of numbers. Or I can have a finite. Right? So I can say like n goes from 1 up to whatever, 50. This is a finite sequence. So you just really want to think of these guys as a list of numbers in a certain order. So, for example, AN if I say n goes from 1 up to 5, you think of this as just a list. A1, A2, A3, A4, A5. Or I could say AN from 1 to infinity. This just means A1, A2, A3, A4, going on forever. Anything else I need to mention about? Right. Okay. So it's just a list, nothing scary. Don't be alarmed. Okay. All of these guys are just numbers. We can think of AN as a function with input n. So example, I can say AN is, and I can give you a formula for this, right? Like A of n. That's how I can think of it. And I can say something like, for example, I can say AN is the sequence n squared plus 1. And basically what that means is if I were to write out the terms of these guys, n goes from 1 to infinity, basically one at a time I'm going to plug in the n values into that function to get the number I'm talking about, right? So I'm going to plug in 1 into here, I get 1 squared plus 1, it's 2. The next number in the list is when I plug in n equals 2, right? N equals 2, plug into here, then the result is 5. N equals 3, plug into here, the result is 10, and so on and so forth. Because this is A1, this is A2, this is A3, so on and so forth, which I think of as A evaluated at 1, this I think of as A evaluated at 2, this I think of as A evaluated at 3, and so on. Okay so far?
Is there any point in time where the n, let's say, is like 5, but it's really the second term?
Yeah, in theory I can start this at whatever number I choose.
Okay.
Yeah. 1 or 0 is typical. But in theory I could start it wherever.
So if the 0 was right there, then
Yeah.
the first one, like...
Then I think of the first term as A0.
So A1 would be A0 something, like so, right?
Yeah, so it's just, the order just starts counting here, and the first term is whatever that n value is.
Okay.
Not all sequences have formulas for them, but the ones we will be dealing with for the most part will have formulas. So basically a sequence is just, I'm going to describe a list of numbers to you in a certain order by giving you a formula. That's basically the idea. What else? Oh, I sort of abused the notation there. It should sort of really look like set notation. Think of it as a set. Here you have a set with 5 elements. Here you have a set, but it's an ordered set. Make sure you get it. Yeah, so AN is just a set from 1 to infinity. I could just A1, A2, A3. Order matters, but it's just a list of numbers. I'm not really doing anything with the numbers yet. And as I said, some sequences, not all, have formulas. There are some sequences that come from nature that we just like empirically measure things, and then we have this list, and then we have to deal with that list. So another example, I can say AN equals 1 over n for n greater than 1 describes a sequence. I can say something like, list the first 5 terms. What would the first 5 terms be?
1 1/2, 1/5,
1, 1/2, 1/3, 1/4, 1/5. That's basically it. This guy here is your A1, your A2, your A3, your A4, your A5.
That's a harmonic series, right?
No, it's not a series, it's a sequence. Series comes from adding the terms. We're not doing anything, we're just writing them in a list. Okay. I can also say something like, what is this sequence? ln n from n goes from 1 to infinity. What would that look like? 0, comma, ln 2, ln 3, ln 4, so on. Sometimes you will be asked to deduce a formula. So I can say, find a formula for, and I give you this sequence. 1 minus 2 over 3, 3 over 5, minus 4 over 7, 5 over 9, find a formula for that sequence. So here if I say AN, the sequence AN is that list going on forever. What's the formula for the sequence?
N over 2 and minus 1.
Or +1 depending on where you start.
So you'd say AN equals starting at n equals well, if I start at n equals 0, the first term would be 0.
So that's be 2n minus 1 instead of 1. Or n plus 1 on the
2n minus 1, and then start at 1.
Yeah.
For n greater than or equal to 1. So if I plug in 1, what's going to happen here? I'm going to get a minus 1 if I plug in 1 first. So how do I fix that? Yeah? I can just make this n plus 1, and then that fixes everything. Plugging n equals 1, I get minus 1 squared, which gives me a positive. I get 1 over 1, which gives me the first term. Plugging n equals 2, I get minus 1 cubed, which gives me that negative. This would be 2 over 4 minus 1, which is 3. Plugging in n equals 3. Minus 1 to the 4th gives me a positive sign. This is 3 over 2 times 3 minus 1, which is 5. So I get positive 3 over 5, and so on and so forth. So yeah, this would be a formula for our sequence. What?
What?
Someone said something just now. Okay. So, sequence, just a list of numbers in a certain order. We can describe them with formulas because we can think of them as functions. Sometimes I'm going to give you the formula. Sometimes I'll give you a list and you have to figure out the formula. And that's that. Let's talk about convergence. I was gonna do this whole speech about how cool sequences are, and I'm gonna talk about the Fibonacci sequence and all that stuff, but feeling under the weather, I can't get excited enough for the speech. Yeah, the Fibonacci sequence is so awesome, and it's about rabbits reproducing. Whatever. And I was gonna say about the golden ratio and blah blah blah. Yeah, just.
You do it tomorrow. See, I love that stuff, but I
Wait,
hate this stuff. Like I've read so much about that, but I hate this stuff.
Yeah. It has to be done at some point. Let's talk about convergence. That's not a person's name, I'm just saying. It's not a strict definition. A sequence converges to an infinite sequence, and put it in infinite. And defining the word convergence, or what it means for a sequence to converge. When we can think of these guys as functions, we can take limits of them. An infinite sequence, an converges if the limit of an equals L.
Wait, since this is just a list of numbers, so I'm confused. Does that mean, what does this mean? Are you like adding them together, or are you just?
No, I'm not adding them together.
You're
I'm just looking at the list of numbers and seeing, are they getting close? Are all the numbers after some point getting
Okay.
super close to some other number? Right? So remember, I can think of these guys as functions, but they just happened on the integers, right? So it's like 1, 2, 3, 4, 5, 6, so on, right? So let's say the first one gives me 1, then a half, then a third, then a quarter, then a fifth, right? So I'm just looking at what are the outputs going towards. Here I can sort of see it's going towards 0, right? That's sort of the idea. Sequence, they don't have to go towards anything. They can do whatever, and just it can be ultimate chaos forever. But there are times when sequences will actually tend towards something, right? That's what I'm trying to talk about here when I talk about convergence. So this is talking about the convergence of a sequence. All you're doing is finding the limit. Here it's L. So basically, so that's how mathematically you'd find the limit if it exists. A sequence converges to L if after some point all terms in the sequence get arbitrarily close to L. Right? So you don't even have to hit the point, you just get super close to it. And we say that means the sequence converges to this number. Not all sequences converge.
So for the example of AN, the one we just did, it wouldn't converge because of the alternating fact with the -1. But if there was no -1, then it was like
Right, if this wasn't there, it would converge.
To 1/2,
Right, to
right?
1/2.
Okay.
But because this is the converge, it's bouncing up and down between -1/2 and +1/2. So this one actually does not converge. This one does converge. It converges to 0, right? So the sequence 1 over n converges to 0. What else do I want to say about here? Let's move over here. If no such L exists, we say if no such L exists, or L equals infinity, or L is infinite, we say the sequence diverges. So converges mean I can take the limit, it exists, and it's finite. If I take the limit and it doesn't exist, or I get infinity, I say the sequence diverges. And there's nothing new about finding the limits of sequence here. It's just like limits from Calc 1 and Calc 2. So if you remember all those rules, you should be fine. L'Hopital's rules and all that still applies. It's just single variable limits. Like I said, Chapter 8 is a Calc 2 chapter. It's not a Calc 3. It's not a multivariable anything. So we were driving down the highway at 70 miles per hour and we just went to park. Some important properties. Let A and Bn be two sequences. C is a constant, then the following hold. 1. The limit of An plus or minus Bn is equal to limits distributed across sums. We can factor out constants. For sequences, the limit is always as n goes to infinity. So sometimes I'd be sloppy and leave that off. It's always infinite. Limit of A times B is just the limit of A times the limit of B. Provided both converge. The limit of An divided by Bn is just the limit of the top divided by the limit of the bottom. If the limit of Bn is non-zero, that's the fourth property. Fifth property, limits can go over powers, so limit of An to the power P is the same as the limit of An to the power P. Here I'm assuming P and An. There's another theorem that holds that we're going to take advantage of all the time, especially in the next section. Sort of a comparison theorem. Also, theorem. If An less than or equal to Bn less than or equal to Cn. Not really. Using the squeeze theorem. The squeeze theorem is what I want to call it. You can name it. The squeeze theorem applies. Right, so if An is less than or equal to Bn less than or equal to Cn, and the limit of an equals the limit of Cn equals L, then the limit of En must be L, right? So if you're squeezed between the same number, you must be equal to that number. That still works. There's another theorem. If the limit of the absolute value goes to 0, then the limit, the original, must go to 0. There's one relationship that I want you to know about. Sequences are important, but I'm really telling you most of this stuff because we're going to use it later for series. That's our main concern here. What is the limit of something like n factorial over n to the n? What do you think that number is? Does that limit exist? Does it not exist?
Infinity? Doesn't exist?
It's infinite. One of the most faster than exponential.
Technically, that's not an exponential. The base isn't a constant, remember. The base is n. The base is growing as the power is growing as well. So does the factorial win?
I think it goes to 0, right? Because the power
Yeah, the power
is bigger, right?
How do you know? How would you investigate it? What would you think? What would you try?
You have to try out values.
What is n factorial? What does it look like?
It's like 1 times 2 times
1 times 2 times 3 times 4 times 5 times. Okay. And this would be over what?
1 times.
No, I'm talking about it for some large n. What's going on here?
1 times 4 times 27 times.
No, I don't know what the n is. N could be 100, could be a million, could be whatever. I just have n times n times n. N times, right? So I have n terms on top, n terms on the bottom. What's going on here?
It's just infinity, right?
Huh?
It goes to 0.
What's going to happen?
The last n cancels out.
The last n's will cancel out. And then each of these, I can group like that, right? Now by the limit property that I had before, taking the limit of these products is just the product of the limits as long as they exist. What's the limit of 1 over n as n goes to infinity? 0. So that exists, this also exists, this also exists, this also exists, right? This would actually approach 0 as n approaches infinity. So there's a relationship that you would have learned in Calc 2 that we can now sort of put in the final word. Well, almost the final word, I suppose. Order of magnitudes. So there are a bunch of functions that we learned about. Talked about logs, exponentials, polynomials, factorials, and now this new guy, the varying exponential. How do they relate to each other? Like who's the biggest, who's the smallest? basically put them in order of like who would win in a fight if you're taking the limit to infinity. Come again? Right, so something like log n would be super smaller than who? Who's the next guy up? N, right? The polynomial, right? This guy represents logs. This guy represents polynomials. Right? So if you ever have a limit where there's a polynomial on top and the log on the bottom and you're going to infinity, it's going to go to infinity. The polynomial is on the bottom, it's going to go to 0, right? This symbol here means that this guy, when you're going to infinity, gets way huge compared to that guy. He's like nothing, right? That's sort of what we're going to look at, right? So logs is the lowest guy on the scale. Polynomials are the next bigger guys. Who is the next one? Powers, like guys that look like a to the n. Exponentials. Who's bigger than the exponentials? The factorials. N factorials would be next in this list. And as we just found, these guys are up top, right? In the next section and sections to come, we'll be playing around with all these functions. They're going to be thrown in there all at once. You need to know who can beat who if they're ever in a competition.
Wait, what is that last term called? Like the n over n? What is that called?
I don't remember.
Okay.
I'd call it a variable exponential or something. This is called an exponential function.
Yeah.
This is factorial. I don't remember the name for this.
Who's gonna call it a variable?
Varying exponential? I don't know. Exponential with a varying variable base.
I like that. Very exponential. That's one too.
Yeah, I should coin that. If it's not, if I'm gonna copyright that phrase if it's like not already like in wide use.
Do it.
What else do we need to know? Okay, yeah. So here I talk about some important sequences like the geometric sequence and arithmetic sequence is another one. Talk about increasing, decreasing. So yeah, still a lot more definitions to go, but by next time we will finish those and we start series, which is the real fun part where we're going to use this table. And it's going to be a lot of fun. You guys will see. It's going to be a lot of fun. So see you tomorrow. I'm not sure if I'll do MATLAB. Maybe I'll do a MATLAB.
12.7, right?
12.7 is due. 8.1 I didn't finish.